It's not.
Okay. The light is not great, so I don't know if you can see anything on the board. There's not much I can do, I'm afraid. Anyway, let's start. Since we can do something now, let's start with one more exercise on the deal folder, and then we'll do all the rest of the pericyclic that I was preparing for today. So think about this one, and think about this is a typical exercise that you might find at exam. So think about the radiochemistry of this compound, of this reaction of the product, and place the partial charges to help you out understanding which one is the HOMO, which one is the LUMO, and what is the final product. If you can place all the partial charges on this one, I'm absolutely sure you can do all the exercises related to this part, okay? Then we'll do all the rest of the cyclizations. Think about this one for a couple of minutes, and then we'll carry on because we lost 20 minutes because of technology. So, where do you start putting the partial charges? Partial charges mean delta minus, delta plus. If you want to put minus and pluses, I don't like it because they're not real charges, but I will accept it at exam. But if you put delta minus and delta plus, it's better. So let's do this one. So I hope you got this one, something like that. Another very important thing that I will typically ask in my questions at exam is when you start placing the curly arrow, when you start using the curly arrows to start the mechanism that forms the pericyclic compound, the cyclic compound, it's always necessary that you start from the HOMO that goes towards the LUMO. Even if the result is the same, if you start from the LUMO that goes with the HOMO, this is wrong. So please use, this is always electrons that move from something where there is a high electron density towards something that goes towards a lower electron density. So whatever you do, once you identify which one is the HOMO, which one is the LUMO, what you do is you start with the arrows that start moving from the HOMO towards the LUMO. So why is this one the HOMO? Diene, the HOMO is normally on the diene and is always electron rich. So diene is electron rich, it has two sets of double bonds, so 4 pi electrons. If you start placing charges, you will see that especially what I suggest is you start from the LUMO, so from the diene part. You start, if you have a good electron withdrawing group, you start putting the strongest delta minus here, then the plus all around. Then you do the movement of the arrows, and then you do the final product. Now, I have to rush a little bit because we lost 20 minutes. But what we saw in the last video is sometimes the 2+2 cycle addition, so the wonderful 4-member rings, can be done, but either you do it photochemically, which means that one electron of one of the two double bonds must be promoted to a pi star, so that becomes your new HOMO for that reaction, for that compound, or you have to use particularly highly activated compounds. So on the first one, we saw that if you want to promote that reaction to form the 4-member rings, let's think about the 4-member rings. We always said that creating 4-member rings is very difficult for both the entropy and enthalpy point of view. So the 4-member ring is very compressed. the 4 atoms don't have the bonds, the angles that they would like to have normally, so they deviate from tetrahedral drastically, so they don't want to form the 4 member rings for that reason. Plus, the 2 starting materials have very high energy, and the final product also has very high energy. So it's very difficult normally to form 4 member rings. 2 plus 2 cycle additions, either photochemically induced or in the way that we will see in a couple of slides, they are possible. And it's very important because 4 member rings are present in all or almost all biological pharmaceutical active molecules. So you need, especially beta lactams, for instance, you need to have this kind of structure. So you want to have something that in the lab will work efficiently to form these 4 member rings. So one of them could be photochemically induced. We saw that in the first part of the cyclizations, the pericyclic, that when you photochemically induce, you promote 1 electron from the pi star from your former HOMO to what it was the LUMO, which now becomes your new HOMO, okay? So in this case, you can form these ones. It's all aliphatics, so this is the worst case scenario. So what happens with the orbitals is that if this is the ground state of the alkene, you have the two electrons in the ground state, in the pi. It is true for both of them because you have 2 different but similar pi bonds. If you promote one of those using UV light, if you induce with energy, you promote this one on the pi star. Now this one becomes your new HOMO on only one of the molecules, the molecule that has the highest possible energy, because the one gets excited first. What happens here is that this one now becomes on one of the 2 double bonds, only on one of them becomes your new HOMO. The other one stays on the ground state, otherwise this reaction won't work. And this is why these reactions are anyway so difficult, because exciting only selectively one of them is not always easy. So this is the configuration of the new HOMO. If you then mix and match with the LUMO of the other one, you see that now there is potential matching to form sigma bonds. Now, if you combine the excited state of one with the ground state of the other one, you lost the problem of not having the right energy. So this is a way to form 4 member rings with the 2 plus 2 cycle additions, okay? This is one of the ways. The other way is, again, when we say that these reactions are not possible, it doesn't mean that they're never possible. It means that they're rare. And rare means that sometimes you need to use very activated compounds to do the same reaction. You saw that in the video, hopefully. One of them is, and this is a typical compound that you want to form, a beta lactam. If you think about from the retrosynthesis point of view, which is always what you need to do in this course because you will use retrosynthesis so much, is you can disconnect in 2 parts. Either on this one, you can connect the 2 carbon-carbon, the carbon-carbon bonds and the carbon-nitrogen bond, and you form an imine on this side, so a nitrogen with a double bond, and a ketene. So this is the very, very, very activated species that you want to use to form this bond, okay? So with the ketene, it works. Otherwise, you do the carbon-carbon, carbon-nitrogen, but in this horizontal way. So in this case, the 2 double bonds, the very activated species, the very, very high energy species is the isocyanate. The good news is that they both work, okay? These reactions both work, so both of them efficiently form new 4 member rings. Let's see with examples. On this one, first you want to form the ketene. Do you have an idea how does it work? I use a base, a very common base. Nitrosamine is a very common base. But let's focus about the base. So the base can abstract 1 proton because if it wants to act as a base, it needs to take a proton. What kind of proton do you think what kind of protons are very easy to be removed in this molecule? Yeah?
Yeah.
Alpha.
Who's alpha?
Alpha to the carbonyl. So the first carbon after the carbonyl is normally called alpha. So the alpha protons, we saw that in so many examples last year. The alpha protons of these kind of compounds are very acidic. This one is particularly acidic because if you have an acyl chloride, remember also the energy of the carbonyls. Acyl chloride is probably the form of the carbonyl where this carbon is the most electrophilic. So these ones are the most acidic protons you might have in a carbonyl molecule. So if you take with a base one of those, what happens? We also have the chloride. The chloride, like we always use it as a good living group. Halogens are normally very good living groups. So what happens here is that you take one proton, kicks out this one as a living group, and you form this very activated species. Okay, this is a ketene, like the one that we saw here. Remember, the ketene is this one, not the imine. So now, this one is so high in energy that no matter the position of the orbitals, it's not important anymore that the position of the orbitals doesn't allow the formation of a four-member ring, because the LUMO of this one is so high in energy that eventually works to form the beta-lactam. And if you see that, now this is a specific example from the Claydon, but there are papers, lots of scientific work has been done around these kind of reactions. And all of those have very high yield. Remember that 90% yield in a chemistry lab, in organic chemistry, is a miracle. So this one shows how efficient this kind of reaction is. Of course, if you want to talk from the practical point of view, from the lab point of view, I have to say that whatever compound is very reactive also produces sometimes side reactions. So from the practical point of view, probably both of them have to be reacted. This one is created in situ, but is not isolated, and it creates the four-member ring straight away in the reaction. So some of those are very difficult to isolate. They are too high in energy. Okay, this is an example with the ketene. This one is the same example, but with an isocyanate. So you can form isocyanate in the same kind of way. What you need to do here is that once you have a compound with very high energy, the formation of the four-member ring is still allowed. Okay. This is very important from a pharmaceutical point of view. Then you can do more chemistry, because sometimes you put these groups, but this is not the final molecule you want. Sometimes you put this sulfonyl chloride just to remove even more electron density, make it even more reactive, but then you don't need it in the final reaction. So what we will do for all this kind of reactions is that eventually you do some more chemistry. In this case, a quick reaction with a very mild base and water removes this activating group, and then you have your final beta-lactam, because the beta-lactams are very strong. Normally are very good antibiotics. At least I would say that most of the antibiotics contains beta-lactam in some form. So having these kind of reactions and producing them in an efficient way is very important. Okay. So message to take home for this one. Photochemical induced, it may work also with aliphatic, so carbon-carbon bond formation. Otherwise, you must have something which is very activated. Ketene and isocyanate are typical ones, for instance, to make beta-lactams. There are other reactions which are very similar for other kind of four-member rings. Let's focus on this one, because at this moment, I prefer to focus on the mechanism of the formation rather than on the variety of compounds that you can make. Okay? Let's do this one. Now, on this one, first, you will need to do the reaction, and then you need to do some extra chemistry. This is something that I might give you in the exam. Again, this one is straight from the Claydon. You saw that the exercises from the Claydon sometimes are more complicated than the one that they give you at the workshops at the exam. Again, if you can solve those, you'll be ready for the exam. Think about, please do the mechanism on this reaction, think about the stereochemistry, because then you want to prove that this stereochemistry actually is the one that specifically works after the formation of the four member ring, okay? In this case, you must use UV light, because with the carbon-carbon bonds, you cannot form something which is so high in energy that eventually will form the four member ring efficiently. So in this case, you must go via excitation with a source of UV light. Then you need to do the second reaction. The second reaction does not involve the four member ring anymore. This is a simple organic chemistry, I would say. We'll discuss this later. So I can see that from my video that you probably, whoever is watching the recording will not see the whiteboard, the projection. So my suggestion is, if you want to watch it again, watch it with the slides, so you know what we are talking about. Okay. I hope that will solve the problem. I'll report the fact that it doesn't work on this one. I hope that for next time we'll be in this class will work. So, first of all, after UV light irradiation, you form your four member ring. Now, you know that this mechanism normally is suprafacial. So, if the two ester groups come from the top and the cyclohexene comes from the bottom, or the other way around, works the same way, the mechanism is suprafacial. I have to say, okay, we'll discuss later, but I have to say that the approach of the two molecules suprafacial is different from what we call suprafacial or anterofacial for other kind of cyclization. And sometimes suprafacial is used in both ways, but in this case, suprafacial means that the two molecules approach from this side, not in a mixed way. That's why the stereochemistry here is absolutely preserved. So this is what happens because of the suprafacial. Remember, in cyclizations like that, if you watch the video and if you do some exercises on the DL solder, on this one, the endo-exo configuration is not important anymore. Only on the DL solder, especially the 4+2 DL solder, the endo-exo is very important. On this one, it's not important anymore. The stereochemistry is dictated by the approach. Okay. We have the formation of four member ring. Now, what do we do? Why you want to do that? So you have the second part of the reaction, which involves sodium borhydride. If you have sodium borhydride on this molecule, what do you reduce? This is important because you will use it when you need to do retrosynthesis and you do the forward synthesis. If you have to do a reduction, you need to tell me what reducing agent you're going to use, because depending on what reagent you're going to use, something works or something doesn't work. So in here, I'm telling you sodium borhydride. Why? I'm telling you specifically sodium borhydride and what does sodium borhydride do to this molecule. Think about it. What does it do? Sodium borhydride. It's a reduction, but you have two possible groups because you have two ester groups, but they are the same. So we have one ester group and one carbonide. What does sodium borhydride reduce specifically? It reduces the carbonide, but often also the ester group as a carbonide. It reduces only the ketone. So sodium borhydride, another borohydride, there is a variety of borohydrides. But sodium borhydride specifically here is fine. But sodium borhydride reduces down the ketone, but it doesn't reduce down the ester. Okay, if you use, for instance, in this reaction, lithium aluminum hydride, because you tell me I need to reduce down the carbonide, be careful because lithium aluminum hydride will reduce both the ester group and the carbonide. Sodium borhydride, sodium cyanoborhydride, Dibal H, all the hydrides, derived from boron normally are not strong enough to reduce down the ester group. This is something very specific, so that if you're in the lab and you know, I have an ester group and a carbon, I want to reduce the carbonate of the ketone, I must use something like that. Then, why this reaction then proves sodium borhydride that you have the right stereochemistry on these two ester groups? Why do you think? Okay, we're doing the reduction of the hydroxyl group. Think about what is the final product and think about it. So here we're saying we're going to use sodium borhydride, we reduce something, and that reduction proves that this stereochemistry is exactly the one that we predicted. Why does it work? Because only if you reduce down this hydroxyl group, which now comes from this direction, only if the two are close enough to each other, the alcohol that you're going to form here, the anion, the alkoxide, only if they are in this exact position, so with that stereochemistry, only in this case, you will have the possibility of the formation of the lactone. Can you see now? So only in this case, if this one was a mixture of, let's say, cis and trans, this one, let's call it cis, because the cyclohexane and the ester groups are coming in the same direction. So let's call it cis. If this one is in cis, it works. If this one is a mixture, we will have, let's say, 50% yield. If the one selectively goes trans, that reaction will work. So even if you do the reduction of the carbonyl to alcohol, that reduction will not form the lactone. In this case, it forms the lactone. That proves that those ester groups go specifically in that position, in cis position with the cycle 6. Okay. In this form, think about it. This one is quite complex, but I might ask you something like that in other kind of exercise. Okay. Think about this one now. It's another kind of transformation. This time is other chemistry first and cyclization later. Think about this one. This one includes also the movement and the rotation around the bonds that we were talking about in the other cyclization lecture. So in this one, you have this alcohol, lots of double bonds. And I gave you chromium 7. What is chromium 7 doing normally? Chromium, yeah, is a very strong oxidizing agent. Okay, so if you have this molecule, you have an oxidizing agent. I can tell you that if you try to cyclize this reaction straight away, nothing will form. After oxidation, something will form. So that oxidation, what does it do?
I was going to say, it also oxidizing agent. I'm sure it would be chromium 6.
Chromium 6 and chromium 7. Chromium 7 is even stronger. Chromium 6 works that way. I did say this is chromium 6. Because I will use chromium 7. But chromium 6, yes, it does work. All right, chromium 4 is difficult. But chromium 6 and chromium 7, they both work. Sorry, I thought I put chromium 7. So, anyway, what do you oxidize? So ideally, there is not much. Oxidizing double bonds is not that easy. So what you want to do first is with chromium 6, not chromium 7. But chromium 7 will work even faster. You oxidize this one. Now, why this one changes everything? Think about the other. So why this oxidation is important?
to be a lot more.
That's partly correct. I mean, you're going the right direction. So if the carbonyl becomes more electropositive, what does it do to the double bond? Think about the DL solder. What do you need to have on the DL solder so that the dienophile is activated? That's correct what you're saying. So the alcohol, as is an electrodonating group or as an electron withdrawing group? Okay. So alcohol is an electro-withdrawing group, an electro-donating group. If I turn it into a carbonyl, you remove it to hydrogen, it's higher in energy, suddenly it becomes an electro-withdrawing group. If you have this one as a double bond, if you have a strong electro-withdrawing group, this one is a good dienophile. If you have a diene on the other side, now you just need to rotate the bonds so that it goes in the cis conformation that is typical of the reaction. So if you move these bonds around so that eventually it reminds you of the formation of a potential intramolecular DL solder, that can form a cycle. With the alcohol will not work. Or you need to apply a lot of more energy. Let's say that you need to go to very high temperature and pressure to make it work. But if you turn that alcohol into the carbonyl, now becomes from the electrodonating becomes electro-withdrawing. And that after you rotate the bonds so that you can see a potential DL solder inside, now you can form your cyclase product. Okay. I'm putting this one in a chair conformation just to show you that these two protons have this kind of specific stereochemistry, always because of the suprafacial approach. We will do that a little more, because this is another important thing. Another question that I typically ask at the exam, so work a lot on that, is either tell me the stereochemistry of this new compound, or justify why this stereochemistry happens. Both of them are interrelated. I typically use them either one or the other or both at the same time sometimes. Okay. This one is a DL solder, is a typical DL solder, so the product is endo. Do you remember what endo means and why the endo conformation of the DL solder is so important? Did you see it on the video? So endo, normally, if you do the potential conformation endo or exo, in most of the compounds, the most thermodynamically stable is the exo. Also, in the final product of the DL solder, technically speaking, the most stable compound, thermodynamically speaking, is the exo. And yet it forms the endo. And the fact that it forms the endo is exactly because of the suprafacial approach. Play with the models, play with the software to understand why that happens, because once you do it, once you see in 3D, then you see why this stuff happens, okay? Please work on that because I love to put that at the exam. This is with a model that you can use using an online software, which is free. If you do the model, you'll see that this one in the circle are exactly those two protocols. The website is called MolView. We use it, probably I started using last year. It's a free, I don't remember if you need registration, but it's free, even if you need registration. And you can model your stuff, then you minimize the energy, which is very important in crystallography. Sometimes you want to minimize the energy to understand what is the most stable structure eventually. And that minimization of the energy shows you that these protons go exactly the direction that you will predict just from the theory. Let's try this one. Then I'll carry on with maybe another slide or two, and then we'll do a break. Sorry, I lost too much time today. Let's put this way anyway. I care more. Don't want to I don't want to give away too much, but I care more about Diels-Alder-like reaction than other rearrangements. So in the next hour, we'll do more rearrangements. You can use that, but I have to say, if you want to focus for the exam and the workshop, I care more about you learn how to do Diels-Alder-like reactions than rearrangements. Stigmatropic rearrangement, Claisen rearrangements, they are really important, but not as much as the Diels-Alder. And I would really like that you master the Diels-Alder-like reactions and the other cycloadditions. So think about this one. Now, again, you have two possibilities. One, you have the formation of a product with itself. So something intramolecular happens because I'm not giving you any other reagents. On the other one, on the left-hand side, I give you the base that you definitely need and another reagent. Please explain what's going on. That could be one of the short exam questions, as is. This one is not difficult. So what do we know on this one? What does the acetic chloride and the base tell you? What do we say at the very start of this class? Why would you use a base, and what are the most acidic protons? Always alpha. There is a beta, but the beta are not as acidic, so you don't take beta, you take the alpha. Yes. So the alpha protons are acidic. Once you take out the alpha proton, you have one living group. What do you form here? You form the ketene that we saw at the very start of this class. Once you have the ketene, you have these other double bonds. Again, like in the other case, you need to rotate the bonds so that eventually you see, okay, if I have a ketene on one side and a double bond on the other side, maybe I need to use those to form a four-member ring. Because the ketene should immediately tell you, I want to form a four-member ring. If you can do that, then we'll see what to do in the other part of the exercise. So, base takes out one of the protons, form your ketene. After you break the carbonyl, once you go back to carbonyl, remember always, if you can go back to the carbonyl, any molecule prefer to go back to the carbonyl. Unless there are specific reasons why you want to keep it as an enol. You saw with Joel, we saw with us. You saw that in the lab a little bit last week, if you consider the reaction that was actually happening in your own bottom flask. Sometimes you want to trap an enol. This is not the case. You don't want to trap the enol. You want that to go back to carbonyl. Only if it goes back to carbonyl, having this double bond here forms this very strong activated ketene. The ketene can react with itself. I mean, the molecule with the ketene can react with itself because on the other side, there's a double bond. Put these double bonds close together because only when the molecule is rotating in solution, when the molecule is rotating, only when those two double bonds close to each other, they can form the four-member ring. In this case, we are forming this four-member ring here. And this is, let's call it a thermal 2+2 cycloaddition. So the exercise from the right-hand side is a simple activation of the acyl chloride to form the ketene, reacts with itself intramolecularly to form a four-member ring. Okay, so if you apply lots of temperature, this molecule will form. What if you have another source of a double bond? Now, your ketene is always the LUMO. So the first reaction works exactly the same way. So you have your starting material, your base, you form your ketene, but now, instead of reacting with itself, you give maybe a lot of this one, because you need to give it a lot. A lot, I mean an excess of the other double bond. Then you can have your HOMO on the side. Your LUMO is always on the keting because it's the highest in energy. And then you have the formation of this formula ring with these protons with this specific stereochemistry. We saw that in the previous slide. Why I'm telling you that this one, you need a lot of this one? Because the intramolecular will go faster. Because the reaction on the right-hand side, what might still happen. So if you have a lot of this one, it might react first before doing intramolecular, but you need to convince it. So you may have a mixture. When this one might be quite good yield, this one might be still a mixture between product on the right-hand side and product on the left-hand side. Okay, you convinced? Happy? Whole hydrogen, in this case, the one that I showed in bold, are up. Again, you can use mole view to prove that these are the hydrogens. The one that I circled are the hydrogen here. So if you draw the molecule like you will do with CanDoodle, with CanDraw, and you put it, you build it in this website, and you say minimize the energy, it starts putting the reaction that the bonds the way that they are supposed to be, and you will see that once you follow these protons, they're all up, and that is true because of the formation of this mechanism via suprafascial approach. Okay. Now, very quickly on this one, you saw very quickly because we saw that a little bit last year, and I want to make a break. I want you to have a break, unless you want me to carry on. Break or carry on? I have a just keep going, something like let's get over with. Prefer a break or prefer? So majority.
Well, I'd say keep going.
Right. I think it's split up. So we did short break always. We'll do a short break, but maybe it's shorter than usual. Maybe only 5 minutes. Okay. After this one. So you saw this one last year with me because this reaction forms an heterocycle. Now we're going to see it not from the heterocycle, only from the heterocycle point of view, but we're going to see it from the pericyclic point of view. Because last year I didn't talk too much about the pericyclic mechanism, but are not doing the break yet. After this one. So this one is called a 4-electron component. It's 3 atoms but 4 electrons, because these species must be charged and must be polarized. That's why they're called 1,3 dipolar cycle additions. Only if you get a molecule like this one, which has a permanent separation of charges, you can get the final 5-member ring. Then on the other side, you need a 2-electron component like any other alkene, like we always use. Doesn't need to be particularly activated. The one that needs to be particularly activated is this one, like for the ketene, like for the isocyanate. This one is where your LUMO is. And your LUMO is here and is doable. This reaction is doable only because of the high energy of this one, which eventually forms this compound, which is called nitron. It's not the most stable compound, but it works. You can do, I will leave you this table as this is just a table, don't learn anything by heart, but this table, like all the tables that I'm gonna give you, if you have a look at them when you're doing exercise, they will help. Okay, let's stop for the moment, but 5 minutes only. Now, I left another exercise. The previous set of slides, please use it for home. Please use it for practice, but it's same kind of concept, nothing new. Just remember that very often I prefer to mix what I'm talking about on the topic of that class, the specific class, but mix up with all the rest of the chemistry that we normally use, because eventually you need to use them all. All these kind of reactions on the kind of different topics can be used in organic chemistry. Let's summarize quickly the cycle addition reactions, because I really, really care about this part. So the cycle addition is a one-step. So it's a concerted mechanism. It means that everything occurs on the same pot. It doesn't have intermediates. The cycle additions are normally, if not always, suprafascial. The Diels order are always suprafascial. They can be thermally activated or photochemically activated. The 4N+2, like the dear solder, they are normally thermally activated. So any kind of normal dear solder, like the one that you will do in the lab, it's a cycle addition, thermally activated. If it's a 4N, like N is the number of pi electrons, like information of the 4-member ring. So the photochemically activated is not only the one for the 4-member rings, but probably the 4-member rings are the most important compounds that you want to use for this reaction. They are photochemically activated because of the orbitals, like we have seen. Think about those whenever you are thinking about making a new molecule. So these cycle additions normally are very efficient. We saw very high yield. So the equilibrium moves towards the formation of the product because they're actually forming new sigma bonds which are stronger than the pi bonds. So whenever you're forming new sigma bonds, normally that is the driving force that pushes the reaction towards the right side. The stereochemistry is very important, like we saw. We do some more exercises from the workshop. Please let me know if you need some more. In general, we'll say that all the exercises from the Clayton are good, but any other sources are good to me, as long as you practice. Stereochemistry or the dear solder also forms the endoproduct. We saw that briefly, but actually you can prove it by NMR. We will see NMR next week, but I mean, for proving the endoproduct is endo, not exo, is not that easy, but it's doable. So this is the very general thing. Remember also the regiochemistry of these cycle additions, okay? Because that's very important because it's intermolecular. The cycle additions, like the dear solder, are intermolecular. So you have one component, the diene, one component, the dienophile. Depending on the distribution, the spatial distribution, you can have either one isomer or the other. Like the stereochemistry is normally quite strict and quite easy to prove. Also the regiochemistry. For the regiochemistry, you place the partial charges. When you place the partial charges, you identify where your HOMO is, where your LUMO is, then you know immediately what is the regiochemistry. So what potentially of the two isomers you're going to form. Now, stopping on the cycle additions, we'll do very quickly, well, not very quickly, but for the rest of the hour, we'll do either pericyclic reaction, because either Poisson rearrangement, sigmatropic shift, these are reactions that actually happen. You want to consider that sometimes some of these reactions happen as a byproduct. So how they discover, researchers, scientists, they discover sometimes this kind of mechanism because they found something that they didn't expect. Because rearrangements are not something that you can always predict. Once you get the mechanism and you can reproduce it, you can always predict for a future one. But at the beginning, for instance, this kind of rearrangement is the typical Clayton rearrangement. It was found because something went wrong. They didn't expect that. We'll see the mechanism in a slide. But now we're considering, I'll let it on the video. You're going to use this kind of compound, the acetals of the aldehydes, for a very good reason. The aldehyde is too reactive sometimes. It's also quite toxic, but the most important thing is that it's too reactive. Sometimes, for instance, I don't know if you saw in any other parts the use of aldehyde, the formaldehyde, which is the simplest of the aldehyde, very often is cyclizes to form paraformaldehyde or other kind of polymer-like aldehydes. So they're so reactive. Sometimes when you trap into acetals, if you remember from other lectures, also with me, they are very often used as a protecting groups of carbonyls. In this case, it also works kind of a protecting group of the carbonyl, so they prevent the aldehyde to react too quickly. This is what you want to use in the lab very often instead of the pure, very short aldehyde, because of hazards, because the aldehyde itself is quite toxic. Remember that whatever is very toxic, whatever is very reactive, might be toxic for your organism because it will react with your, I don't know, your DNA, with your organs. There is a variety of these acetals. That's the acetal of the aldehyde. Sometimes you need the acetal of the ketone, or sometimes you need the aldehyde of the acetal of the ester. In all the cases, when you mix up with compounds like this one, this enol, then you can form the first reaction. So when the nucleophile attacks the former carbonate, we will see in the next slide. So this one here and there is a former carbonyl, but remember, the electrophile is there, the delta plus is there. So the nucleophile here is not the best nucleophile ever, but the hydroxyl group in this case can react as a nucleophile, attacks the carbonyl here, kicks out one of the living group, and forms very activated double bond. This one is not stable enough, rearranges, and forms what is called the Claisen rearrangement. So the Claisen rearrangement follows the 3 arrow movements that we saw for all the other cycloadditions and pericyclic reactions. Okay, so think about it. When it forms, it rearranges immediately and it forms the ketone product. Why does it form the ketone product? Always the same reason. If there is something which used to be a carbonyl, or it prefers to be carbonyl, normally it goes to carbonyl. It turns into a carbonyl. There are acetals also for other compounds like amides. Now, let's see why this one is a very useful, very, very useful synthetic equivalent of aldehyde. We say that because acetaldehyde is quite toxic, but also is very reactive. So sometimes you want to slow down. That's why you use protecting groups, either because you want to prevent a reaction or you at least to slow it down so that another reaction occurs first. So this one is very useful. How does it work? You have the acetal, you put it into acidic conditions. Once you put in acidic condition, what is the first thing that happens to these compounds when you put it in acidic conditions? That's basic chemistry we started from the very first year. You put a compound like that, you put in acidic conditions, what happens? Protonation. Acidic conditions, if it's possible, remember the typical rule of the acid and bases is that if they can do something, if it can react as an acid, it will react as an acid. If a base can react as a base, first it reacts as a base. Then maybe it might be a nucleophile, but first it reacts as a base. In this case, the acid reacts as an acid. Protonase that. Why is important? Because the living group will be methanol instead of the methoxy. Methoxy, in certain reactions we saw when you use esters, for instance, the methoxy is a decent living group, but it's not the best living group. If you activate it with an acid, that the next reaction goes faster. So what you do, pick out methanol. Now this one in situ, because this is not a compound that you will isolate in the lab. Now this one in situ is a very strong and very electrophilic carbonyl. Now even an alcohol, which is a horrible nucleophile, can and will act as a nucleophile. The alcohol attacks the carbonyl. Remember that whenever we put a positive charge, because the oxygen has 3 bonds, no matter if the positive charge you start in the oxygen, which is not incorrect if you do it in the exam, but you know that this positive charge doesn't like to stay there and basically forces this carbon here to be much more electrophilic. So the delta plus, eventually the plus, almost proper positive charge, moves on the carbon. So the hydroxyl group attacks, you get a protonated version as well. Now you can, with whatever you have, methanol for instance, even just methanol gets protonated, taking out this proton, and this one gets methanol. Now what do you need to do? You're still in acidic conditions. What happens? Protonate the other methoxy, and then eventually via elimination, you form the double bond. Now you form your first part. This is the first reaction that happens. Of course, this one is not stable enough and rearranges. It does the Claydon rearrangement that we saw before, so that it forms the carbon atom. But now, let's focus on this one. You will use this one in the lab. I don't know if it was this one or the amide one, but anyway, an acetal compound. Now that we know a little bit about Claydon rearrangement, let's try to do this one. Again, rotate the bonds and tell me what happens. So now what we need to do is find out where the R groups, whatever the R groups are, whatever big or short, could be proton, could be a methyl, could be whatever else. But I would like you to consider, according to the rotation of the bonds and the potential arrangement, what is the final molecule? So you have one double bond. What do you think is the other double bond involved in there? Because you need to have two double bonds to do a Claydon rearrangement. It's a silly question because the only double bonds are on the aromatic ring. But remember that the aromatic rings, they sometimes react as a double bond. The only difference is that then they want to go back, like the carbonyl wants to go back to carbonyl. Aromatic or former aromatic groups prefer to go back to aromatic. So first thing you might want to do, rotate these bonds. You want to put it in a way that reminds you of what we're going to do, a rearrangement, a Claydon-like rearrangement. Now, you have two double bonds in a position that reminds you of the previous one. So these two double bonds, you now need to get a carbonyl. Where does the carbonyl? Okay, the carbonyl forms here, breaking the aromaticity. If the carbonyl breaks the aromaticity, it forms this compound. If you do the rotation right, those R groups can be only in that position. What happens now? Yes, the carbonyl, we saw that the carbonyl, whenever you can form a carbonyl, prefers to form a carbonyl, but also whenever you want to form, you can form an aromatic group. It prefers to go back to aromatic. So this one loses aromaticity. Which one do you think is the lowest energy, the carbonyl or the aromatic group? So if the molecule has to choose whether to stay as is, as the carbonyl, or go back to aromatic, what does it do? It goes back to aromatic. Carbonyl, yes, it's very stable, it's very nice, it's very versatile. It's probably my favorite functional group in organic chemistry because you can use it for anything. But if you break aromaticity, it prefers to go back to aromatic. So that's why I've highlighted this proton. Something like the solvent might take this proton. The two electrons that form the bond between carbon and hydrogen goes to restore the aromaticity, and this one stays as a phenol. We saw that when we were discussing about potential enols. So the only one that is, you will never form, not even in a 0.something% in form of ketone, is a pseudo-phenol. Phenol is far more stable. So it will always go back to aromatic, okay? So, rotation of the bond, again, for future exercises, always try to rotate the bonds in a way that reminds you of the mechanism. Because you can see it even from the open structure. Once you learn it, you can say, okay, this double bond goes there. And then you switch it, automatically happens in your mind. If you're not sure, please rotate the bonds, and then you do the rest of the reaction, okay? Now, let's go back to side reactions, because sometimes I've anticipated some of these movements of rearrangement of double bonds consider side reactions because you want to have something pure in that form and you're going to mix them. Or you get completely the wrong product. So follow the deuterium. The deuterium moves the same way as a proton, but it's easier to follow. So there is a lot of chemistry, a lot of analytical chemistry that is done following isotopes. Deuterium is one of the common ones. So what happens? Can you see any of the mechanisms? Plenty of double bonds. So in this case, you start with these two double bonds. Try to do a rearrangement. It's called sigmatropic rearrangement. It's exactly the same concept as the Claisen rearrangement. Only this one happens in the same molecule. It doesn't break the cycle. So you follow the deuterium. 3 arrows, okay, the deuterium moves here. The same way as we did with the Claisen rearrangement. The deuterium moves with the 2 electrons, so it's like a hydride shift. The mechanism of this kind of reaction is exactly the same as a hydride shift. So when you see the beta hydride shift and the cross-coupling reactions that we saw in the past classes, the movement is the same. Sometimes, normally, these ones, deuterium, like has the same chemistry of the proton normally. It prefers to move as a positive. If we can rearrange in a different way, sometimes happens that it moves with the 2 electrons and leaves the positive charge behind instead of the negative. We saw that in many other reactions, many other potential arrangements. Do you remember a very particular one that we saw in the, I think it was the first year? Formation of potential primary carbocations. Remember when we rearrange, the carbocation rearranges because the primary is too unstable. If it has the possibility to become secondary or tertiary, something moves with the electrons, which is normally not allowed, and it forms a secondary or tertiary carbocation. It's the same movement of electrons. Remember that eventually chemistry, like follows nature, tries to go to the lowest possible level of energy, tries to go to the ground state. It doesn't always happen because otherwise we wouldn't be alive. If everything goes to the ground state, we wouldn't be alive. Fortunately, there is a nice equilibrium between excited state and ground state. But this is what happens. Then, once the deuterium goes there, this is just for practice. I don't want you to be confused or to panic with the number of Cagliaros moving here. But at some point, and this is something that we saw in other reactions with the aromatic groups, especially when you have to justify with the resonance structures what is the most stable or the most likely substitution on an aromatic ring. The same here. When you involve the aromaticity of this group, you have to move the double bonds around, which eventually are double bonds. They can move around. That's why the aromatic one is so stable. Once you go in this direction, you can always get that, and from that, eventually, you can put the deuterium here. Now, the point of this exercise is that I want to show you that sometimes you start with the formation of a product, you end up with a horrible mixture. That happens so often. Sometimes these reactions are almost impossible to control because of the equilibrium between one form or the other. I don't remember if I left it, but I normally put this one also on the workshop. So please have a look. On the workshop, you'll have one question assessed. The others that I leave only for practice. Please do the practical one as well, okay? Eventually, you've got a form. Instead of one single product, you might have a mixture of 3. And only with the deuterium, the presence of the deuterium, you know that this one is actually moving. It's quite dynamic. It's not fixed. And that's why sometimes it's seen as a side reaction. Now, let's try to do this one. Let's play with the mechanism of this reaction. So, try to do the Claisen rearrangement, so the movement, the rearrangement of these double bonds, and tell me how the hell it works in para. Think about as well that nature wants to go to the lowest possible state of energy. When they can do it, they do it. Practice with the movement of the arrows. So what happens first?
It's less.
So do you think that this group, you have, again, like most of the exercises, I always tell you, have a look at the structure of the product. If I give you the product, have a look at the structure of the product. Do you think this one breaks and goes straight here in para? Or is a stepwise reaction? Stepwise, I'm not sure you can isolate it, but stepwise, at least it goes into different steps. Stepwise, sometimes it means that one of the intermediate can be isolated. No, this is not the case, but still it's in two steps. So it doesn't break completely, and then it moves straight to the para position, because that will be silly, because that means that this compound is not stable at all. But think about if you have, I'll give you another hint. Think about if you don't have the methyl groups next to the hydroxyl group, what happens? If you don't have those, then we'll see when you do have. Yes, this is a Claisen. So if you put those in the position, if you put the double bonds in the position that reminds you of the typical Claisen rearrangement, or a typical pericyclic reaction, because eventually, forget it is a rearrangement, it's another pericyclic reaction. So the typical movement of three arrows concerted, so all at the same time in the same molecule. That one now is not aromatic anymore. We saw that. Now we can take a proton and it becomes aromatic, everybody happy. If there is a methyl group, you do the same. Of course it happens. What proton you take now to take go back to aromatic? You don't have a proton here anymore. You don't have a proton here. You don't have a proton there. What is the next proton you might use? The one in the meta position. No. Say that. If you rotate the bonds, and if you use this double bond, because the other proton, the one that I wanted to show you, is this one. The proton here, I'm not saying explicitly, but if you take out this proton, it goes back to starting material, to the two starting materials. But if you want to form the product, then you rotate again. You involve this carbon, so not the proton in meta, but you do use this between the meta and the para carbon. But this one, if you rotate the bonds so that eventually it reminds you of another Claisen rearrangement, if you arrange it in this way, now you have this proton. Now, if you eliminate this proton, you can restore the aromaticity so that eventually you have your phenol. I'm using that only for highlighting the movement of the Carli arrows or the pericyclic reaction. I hope I'm not confusing you. Please let me know. Please ask me if something is not clear. So on this one, you rotate the bonds. Follow only the first exercise. You rotate the bonds and you do the first potential Claisen rearrangement. Now you have two possibilities. Goes back to starting material because it takes this proton, or rotates. Since there is free rotation at some point, you'll get this configuration. And now you use these two double bonds to put that in para to the original oxygen, carbon-oxygen bond. Now, an elimination. Now, anything, even a solvent that can take this proton. Remember that anything that can take the proton to restore aromaticity will do. It doesn't need to be a great nucleophile, it doesn't need to be an excess. Anything will do. Even humidity will help to restore aromaticity. Now, this one is in the perfect position to get him. Try to follow. I'm not doing it, but try to follow the potential movement. Two electrons that form the carbon-hydrogen bond moves here. This double bond resonates, breaks the carbonyl to form the alkoxide first. Now, once you form the alkoxide, this one stays aromatic because it really likes to be aromatic. And you have an O-, and at some point, again, any solvent, even moisture, will give the proton to form the phenol. Okay? Please practice with this stuff, guys, because if you take the slides, you redo the exercise, you use the solution, you think you know, then once you go to the white paper at the exam or the workshop, it's not as easy. So please practice a lot so that once you see the exercise in the exam, it sounds familiar. This stuff requires practice. Quick follow-up on factorization because today we finish with pericyclic. If you remember or don't remember, this is where I'm starting reconnecting what I'll say suprafascial or anterafascial because it's different. This concept is different. The suprafascial anterafascial here is different from the concept suprafascial approach to do the deal solver. Here, suprafascial means something different. So if you can do cyclizations now, you remember this table. Now I'm adding anterafascial or suprafascial. But you will immediately now, I hope you will immediately connect with what I'm talking about. Remember the table that I used at the beginning? The number of double bonds, either thermally induced or photochemically induced, that do one the opposite of the other. So, for instance, odd number, normally, if you build the molecular orbitals and you find your HOMO and LUMO, odd number normally is a disrotatory suprafascial mechanism. In this case, suprafascial is not the approach, the 3D approach. The suprafascial in this case means, if you remember how to build the molecular orbitals, suprafascial means that the two loops of the same sign are in the same direction. So there are two different kinds of suprafascial, okay? I don't want you to get confused with that. So suprafascial here means that if you do the molecular orbitals, practice with those as well, the two electrons are, the two lobes of the same sign are on the same side. Same sign and same side, suprafascial. Anterafascial, it means that one of them is in one direction, one of them is in the other direction. And that dictates that predicts and dictates your stereochemistry. So odd number, suprafascial, this rotatory mechanism, because when they are suprafascial, remember, to form a new bond that eventually will form the cycle, one moves one direction clockwise, the other one anti-clockwise, or the other way around. So the movement is disrotatory. If it's suprafascial, it's disrotatory. If it's anterafascial, it's conrotatory, because one of those means that both of them needs to move in the same direction to form a sigma bond. So the first one, thermal cyclization of conjugated tetraheme. Thermal tetraheme for anterafascial conrotatory. Okay? If you do that, take the exercise again. Please do that and confirm that this is the correct one. Okay? Don't believe me. Practice with that. Second one, photochemically induced of the conjugation tetraheme. Photochemical is the same conjugation tetraheme it has to be the opposite. If you do that, if you build your psi with the molecular orbital, you will find it. It will become even number, tetrahene, antarafascial conrotatory, thermally. The opposite, even number, is suprafascial disrotatory. Still, it's a 4x4 cycloaddition. 4x4 photochemical, again, has to be suprafascial disrotatory. This is an example of a 4x4. Those are reactions that we can do in the lab very easily. If you have the right relation of the UV lamp, anthracene, there are two molecules of anthracene. So the same molecule reacts with itself to form the kind of very nice molecule, which I really love because my chemistry works a lot with this kind of rigid and contoured molecule. This is a very easy way to form this kind of molecule. Last example, 2x6 thermal. Again, 2 electrons even has to be antarafascial conrotatory. So if you do this kind of reaction, for instance, you build your molecular orbitals, you will see that the loops are going to be antarafascial, so one on the one side, one on the other. So the movement to form a new sigma bond, which is here, this time you need 2 new sigma bonds, but because this one is a 2 plus 6, it's not just the normal 4x2. But whatever happens, the pericyclic reaction works always the same way. So it's a 2 plus 6 has to be antarafascial and conrotatory. Now, very last part. I want to show you on this one, even going back to also to the molecular orbital, but even without using the molecular orbital, I would like to show you the conformation of these compounds and why certain reaction works better than others. Some certain rearrangements work better than others. So you have this starting material on the left, you heat up, and when you heat up, you know that you can have a pseudo chair with the R group either in equatorial or in axial. What is the most stable? So this one is open. It's not a 6-member ring, so it's not exactly a chair or a boat. It's a pseudo chair or pseudo boat. In this case, the most stable one is the pseudo chair. Pseudo chair means that you might have this R group either in axial or in equatorial. Which one is the most stable? The one in the equatorial, where the R group is in equatorial because the lowest energy. So if you have this kind of chairs and you want to do the rearrangement, you get that if you have axial, the R group in axial position, you have a Z double bond and is disfavored. So the new double bond you're going to form is Z and is disfavored. Instead, if you start from something which is far lower in energy, this one is stable. How do you work? Try to work out this one and tell me, what is the conformation of your double bond in unstable position? You might have the double bond that could be EE or ZZ or neutral. Think about that. Try to play with the chair, pseudo chair. So you can see the sigmatropic arrangements, like the Cleveland ones, as a pericyclic reaction, but that doesn't form a new cycle. It was open, it stays open. Only it uses the same kind of chemistry, the same kind of movement of arrows to explain why you're rearranging in such a way. Remember that the Carly arrows are all in our imagination. This is the way that we use to explain to ourselves why this product is forming. The good thing about the Carly arrows is that if you can use them, you can explain most of this reaction almost immediately. Only the very strange arrangements are not explainable using the most common Carly arrows. So, have this one. start moving the arrows so that eventually you form a new sigma tropic. This is the one that breaks. Either it's symmetrical, so either you start this direction, even without doing the curly arrows. But even if you, since it's symmetrical, it's easy. You can start from this double bond or this double bond. You move this one around, this one breaks, and this one forms the new sigma bond, the rearrangement. Then you need to try to understand the conformation. Now, shell conformation, the 2 meters, I put it in bold, so both are going the same side. So, if you do the shell conformation, one is going to be in action, one is going to be in equatorial, but both have to be, you can flip them, but both of them have to be on the same side because you draw that. This is the stereochemistry that you assigned. So once you do this kind of shell conformation, you can start thinking about your movement of curly arrows to form potentially. I put it dotted, I left it dotted because it's a potential movement. So if you start from the most favorable conformation, so the lowest state of energy, you put these two, one in equatorial, you form new bonds, you find that the new double bond, remember you broke on this side, between the 2 meters. You broke here, so follow the new formation of the new double bond. One here, one there. If this metal is up, this one has to be Z, so cis. This one has to be trans. If you do this reaction and you try to track it via spectroscopy, you find that this one with the E and that is 99.7, let's say quantitative formation of exactly this stereochemistry. The stereochemistry of this double bond is basically exactly the same. You have traces of some of the others because it always happens. It always happens that you don't have 100% yield of one compound. And this is only because of the shell conformation of the most stable, potential most stable starting material, and of course, the most stable product. If you want to see the molecular orbital, because we talked about the molecular orbital, you always need to construct your HOMO and your LUMO. So for instance, in this case, they could be seen as is 6 carbons. You can see the HOMO and the LUMO can be seen as the allyl anion or the allyl cation. You use allyl anions and cations already in organic chemistry. But let's focus on the 2 parts. Allyl anion, extra pair of electrons. So to here, to there, side 2, this is your highest occupied molecular orbital. It's most stable of the 2 because the allyl prefers to be negative rather than positive, but there is a lot of chemistry that you can do with the positive allyl cation, okay? So we built our highest occupied molecular orbital. You can do the same with the allyl cation, only this time on the other side you have nothing. You don't have electrons. So this one is your HOMO. This one, the side 2 of this one has to be your LUMO. So the next one, the lowest unoccupied becomes your LUMO. So eventually, with these 2, you can combine them. Lobes of the same side go together to form the new compound. So this one can be the component are both suprafascial, the arrangement. So only in this case, when the 2 lobes are exactly on the same side, you can form a stable compound. This is another exercise that I normally put it on the workshop. If you want, you can try and do it very quickly, and then I'll leave you. All the rest, I don't remember if I have other slides, but if I have other slides, only for more practice. Try to do that as best as you can. Now, remember that the deuterium is something very useful because it behaves like a proton, okay, chemistry-wise, but you can follow the reaction just using the deuterium. I can tell you that one can turn into the other. Can you do Cagliaros to explain why and how one can turn into the other one? I'm not telling you that this molecule is stable. I'm not telling you that this molecule even exists. We're just using it for practice. So if someone says this molecule will explode, you're probably right. In front of your own eyes. But on the paper, everybody's safe. Same reason why, whenever you want to use sodium potassium cyanide in photosynthesis, please do on the paper. On the paper. Do you have an idea? You tried? We'll see it. So you start from this one. What can you do? Pericyclic. We have two double bonds. So we're doing pericyclic reactions. Have a look at the double bonds. These two double bonds form a new four-member ring. If this molecule is unstable, this one is insane. Don't worry. On the paper, it still works. So, for the sake of the exercise, these are the double bonds. So, if something happens, must involve those double bonds. Now, because this molecule is unstable even on the paper, you can turn it into this one. Okay? So, you use two double bonds to do 1, 2 plus 2. Then, with the reverse 2 plus 2, you open up the other four-member ring to form your compound. Then you can imagine you can go back and forth. You can do the same again, and then it turns to this one. That's why I wrote it as an equilibrium, despite the molecule probably does not exist. Just practice. This is just for fun to practice. I don't know if we have a different definition of fun, probably, but to me, it's fun to practice with this one if they don't exist. Because if you can do with those, if you can identify it in one molecule, the positions, so that position of the double bond, so that you can do a pericyclic reaction, I'm super happy. So, for instance, and I don't regret that, but if you do photosynthesis and you show me that a compound can be formed, and then you say, of course, it's not gonna happen, but you are creative enough to show me that maybe it might work if you use that pericyclic reaction, which will never happen. Maybe you're not gonna get the full marks, but I'm gonna give you something for creativity. I'm not suggesting you to be creative and to go through and do something that in the lab will never exist. But I really appreciate people who are creative. Please be creative and plausible at the same time. That's the best part of being a chemist, okay? I stop here. I'll see you in the lab next week.